We now begin a whole new section of our course, Chemical Equilibrium. This is Chapter 15, but it's going to continue into Chapter 16 and Chapter 17 and take us up until midterms. Let's think about a chemical reaction. Here's a chemical reaction of the type we've written about 1,000,000 times. N2O4 as a gas goes to 2 moles of NO2 gas. Reactants go to products. And as we learned in the last chapter, it does that at some rate and has some rate constant, which is K. And actually that's a lowercase k. That's going to be very important because pretty soon I'm going to introduce a capital K. So rate constant K is a lowercase k. Now, up till now in your entire chemistry education, you have written equations this way. What we've ignored is that actually some chemical reactions go both ways. This particular reaction, for example, also goes in reverse. N2 NO2s actually react together to go back to N2O4. And there is a rate, of course, associated with that, which we can call also K. Now, to distinguish between these K's, I'm going to say this one is K sub F for the forward reaction, and this is K sub R for the reverse reaction. Now, usually, we don't actually write the equation twice. What we'll do is write it once with a double arrow. N2O4 is going to NO2, but 2NO2 is also going back to N2O4. When you see that double arrow, you know the reaction is going both ways. To illustrate this concept, let's take a look at this YouTube video. If you want to look at the whole video yourself, you'll see it's called Bailing Beakers Equilibrium in Chemistry Class. Now, the situation here is you've got 2 students and 2 beakers of water. Both of these students have cups, and with those cups, they are going to bail. She's going to dip her cup in the water, take some water out and put it in his cup, and he's going to take some out of his beaker with his cup and dump it into hers. So that's what we're going to watch right now. Now, ignoring the splashing, take a look at what's happening. The water levels in the beakers are not changing. Aside from some of it that they've lost in splashing, you can see that the level of water in the beakers is practically the same. This is because they were bailing at the same rate. Her speed at which she dumped her water out into his beaker was pretty much the same as at the speed at which he's pulling out his water and dumping it into her beaker. Until she gets a bigger cup. Look at that. The teacher is now giving this girl the bigger cup. Now watch what happens. Now the water levels are changing, right? There's a lot more over here in this beaker that the boy has than there is liquid in the beaker that the girl has. Until we reach the point where the only thing she can lift in her beaker is enough to fill his beaker. Because of that low water level that she's got, she can't get enough in her cup to fill it, And once again, they're taking out the same amount every time. You'll notice the levels are not the same, but those levels will now not change, because once again it's going to be equal the amount that's being taken out of this beaker and the amount that's being taken out of that beaker. So what does that mean in terms of our chemical equations here? Well, if we think back to the kinetics chapter and we call these elementary reactions, then we can say the rate of the forward reaction is equal to the rate constant of the forward reaction times the concentration of N2O4, and we can say the rate of this reverse reaction is equal to the rate constant of the reverse reaction times the concentration of NO2 squared. And remembering the video, the two rates are equal. If I am at equilibrium, the rate of the forward reaction must equal the rate of the reverse reaction. This equation is always true at equilibrium. The rate of the forward reaction equals the rate of the reverse reaction. Okay, so that means we can rearrange this equation to look like this. NO2 squared over N2O4 is equal to a ratio of the rate constants, which in fact is a constant itself. Let's think about that a little more closely. The ratio of rate constants, Kf over Kr, is equal to a constant. We're going to call this constant capital K. This is the equilibrium constant. We're going to call it K sub C because we're talking about the equilibrium constant in terms of concentration. This lovely K we're going to talk about for 3 chapters, and the only thing that's going to change about it is this little letter right here, which is just a label. It's just something to tell you more specifically what kind of reaction we're talking about the equilibrium of. So right now we're talking Kc because we're writing K in terms of concentration. Now in general, if you have a generic equation, little a times big A plus B, those are the reactants. A and B are the reactants. Little a and little b are the coefficients of those reactants. And your products are C and D, capital C and capital D, where their coefficients are little c and little d. You can write Kc to be this. Kc is equal to the products multiplied together raised to the power of their coefficient over the reactants, the concentration of, that's what these brackets mean, the concentration of the reactants raised to the power of their coefficients. This is always true for any equation. Of course, being chemistry, there's a couple of exceptions. Notice these are concentrations. If we're talking about a pure liquid, such as water, for example, that doesn't go in here. Water is totally ignored in this Kc equation. If we're talking about a pure solid, we had NaCl dissolving in water. The pure solid NaCl, that doesn't count either. Neither of those things are in this guy. The only things that are in a Kc are solutions. Ions dissolved in water. A couple other things to note about this. One is you'll notice the equilibrium constant, unlike kinetics, depends solely on the stoichiometry of the equation. No mechanisms here, just straight the stoichiometry of the equation. It also doesn't matter how much of anything I've got. It doesn't matter if I start with just reactant and I have no products yet. It doesn't matter if I have some of all of these. It doesn't even matter if I have just products and no reactants. I can always calculate a K once equilibrium has been established. Remember that K is a constant, so nothing changes it. The only thing that'll change K for a particular reaction is temperature. There has to be a different K at different temperatures. But other than that, K is a constant no matter what I do to the reaction. Now, what if we're not talking about solutions? What if we're talking about gases? Well, in fact, there is a K based on pressures. K, amazingly enough, sub P for pressure. This is exactly the same format as the other one, except instead of concentrations, we're talking pressure. The pressure, the partial pressure really, of gas D to the power of the coefficient times the pressure of gas C to the power of the coefficient of product C over the partial pressure of reactant A to the power of the coefficient A times the pressure of reactant B to the coefficient of B. Exactly the same form, except pressures. Now it is possible to convert between Kp and Kc using the ideal gas law. And yes, the ideal gas law is rearing its ugly head in this chapter, so make sure you review those. But using the ideal gas law, and if you are interested, it's on page 636 of your book, you can derive this equation here, which is Kp, the gas constant, equilibrium constant, equals Kc, the equilibrium constant based on concentration, times R, that's our old friend the gas law R, 0.0821, times the temperature, in kelvins, of course. Both of those together, note the parentheses, both of those together to the power delta N, where delta N is the number of moles of gaseous product minus the moles of gaseous reactants. Note that little word gaseous in there. If they're aqueous or solids or liquids, they don't count in this equation. It's only the moles of gaseous products minus the moles of gaseous reactants.